Hello everyone, welcome back to Sulekha physics classes. It is the most easiest way to learn all the concept of physics through this class. Today I am going to start chapter wise most important questions and their solutions. But before that you must know about chapter wise distribution of marks, right? From which chapter, how much marks, what is the weightage of that chapter. Okay, so let us start with unit 1, that is electrostatics, and this weightage of this electrostatics is 8 marks, right? And this electrostatics unit consists of two chapters. One is electric charges and field, and the one is electrostatic potential and capacitance, and these two chapters consist of 8 marks, right? Then second unit, current electricity. This chapter alone consists of 7 marks, right? So the weightage of this chapter is more. Only one chapter consists of 7 marks, right? Then unit 3, magnetic effect of current and magnetism. Again, this unit is divided into two chapters, chapter 4 and chapter 5. That is moving charges and magnetism and matter, and these two chapters consist of 8 marks, right? Then unit 4, electromagnetic induction and alternating current. Again it consists of two chapters and this consists of 8 marks. Then come to unit 5, electromagnetic waves, only 3 marks. Then optics, yes, this optics again is divided into two parts, ray optics and wave optics, and these two chapters consist of 14 marks alone. It means the weightage of this optics chapter is very high. It alone consists of 14 marks. So you have to concentrate more on these chapters, right? Again, dual nature of matter, it consists of 4 marks. Then atoms and nuclei, only 6 marks. Two chapters are there, atoms and nuclei in this unit. And then electronic devices, last unit 9. Again, there is only one chapter, this one, okay, and this consists of 7 marks alone. So it means this chapter is also very important. So you can easily find that from these units 1 to 9, you have to focus more on which chapter. Let us see. This current electricity alone consists of 7 marks. Okay, current electricity chapter. Then optics consist of 14 marks and electronic devices consist of 7 marks. So you have to concentrate more on these chapters. 7 plus 14 plus 7, it means 28 marks from these 3 units only. Current electricity, optics and electronic devices. And then after that, electrostatics 8 marks, and this magnetic effects 8 marks, electromagnetic induction 8 marks. Then last two chapters 4 and 6 marks. Okay, so you must keep in mind about the weightage of chapters. Okay, focus on those chapters which have highest weightage first, right? So after this, CBSE had released a marking scheme for board 2020-21. In board 2020-21, there are 5 sections A, B, C, D and E. Section A consists of 10 questions of 1 marks each and 4 questions of assertion reasoning. It means there are 14 questions in all and each questions consist of 1 marks. It means 14 marks section A. Then section B, it consists of 2 case-based study questions, 4 marks each. It means 8 marks section B. And then section C, short answer type questions, 9 questions of 2 marks each. It means 18 marks. And section D, again 5 questions of 3 marks each. So it means 15 marks. And last section E, there are 3 questions of 5 marks each, long questions, and it consists of 15 marks. So in this way, Marks distribution is there. Total 17 marks, 70 marks, and total number of questions are 33. So it means there are 33 questions in all. After this, CBSE has removed some topics from each unit, okay, for this year only. So let us see what are those topics. In chapter 1, electric charges and field, uniformly charged thin spherical shell topic is removed. No need to study this topic. When you are doing revision, please keep in mind these things, that no need to study this topic. No questions come from this one, uniformly charged thin spherical shell. Then in chapter 3, current electricity, carbon resistor, series combination, panel. These are removed for this year. Then chapter 4, only one topic, that is cyclotron is removed. Okay. Then in chapter 5, magnetism and matter. There are many topics removed from this chapter. Magnetic field intensity due to a magnetic dipole along its axis and perpendicular to its axis. Then torque on a magnetic dipole, para, di and ferromagnetic substances. Then electromagnets and permanent magnets. All these topics are removed. Then from chapter 7, alternating current, power factor and wattless current is removed. Electromagnetic waves, basic idea of displacement current, no need to study about displacement current, okay. Then in chapter 9, ray optics and optical instruments, reflection of light through mirror formula, then scattering of light, why blue color of sky, reddish appearance of sun at sunrise and sunset, resolving power of microscope and astronomical telescope, then polarization, Revester's law, all these things are removed for this year. Then in chapter 11, dual nature of matter and radiation, Davison-German experiment is removed. In chapter 13, nuclear, radioactivity topic, no need to study about this one, radioactivity, alpha, beta and gamma particles, these things, then binding energy per nucleon, these topics are removed. And last chapter 14, Zener diode, this Zener diode is removed, and how it is used as a voltage regulator. No need to study this one. In this way, all these topics are removed. Okay. So, जब भी आप रिवीजन कर रहे हो, इन चीजों को ध्यान में रखिएगा कि हमें ये टॉपिक्स नहीं पढ़ना है इस साल के लिए. ओके. अब मेन जो है हमारा आज का हम शुरू करेंगे चैप्टर वाइज इंपॉर्टेंट क्वेश्चंस. एंड टुडे आई एम गोइंग टू start with chapter 1, that is electric charges and field. Okay, first, actually unit 1, that is electrostatic, consists of 2 chapters, electric charges and field, electric potential and capacitance. आज हम सबसे पहले इलेक्ट्रिक चार्जेस एंड फील्ड्स के इंपॉर्टेंट क्वेश्चंस देखेंगे और उनके सॉल्यूशंस देखेंगे. ओके, सो लेट अस स्टार्ट विद चैप्टर 1, इलेक्ट्रिक चार्जेस एंड field. In this chapter, from the basis of last 10 years, I have selected 7 questions, right? ये last 10 years में सारी questions repeated है, पूछे गए हैं. So all these 7 questions are very very important for the board exams, right? So starting from question number 1, that is state Coulomb's law and express it in vector form. Generally these questions asked in 1 marks, 2 marks and 3 marks also, right? So this question is important for 1, 2 and 3 marks. Then derive an expression for electric field intensity at a point on the axial and equatorial position of an electric dipole. So you must know about what is electric dipole, then what is electric field at a point on axial and equatorial position of electric dipole. This question is also very very important, and this generally comes in 5 marks, right? Then question number 3, find the expression for electric field intensity at a point on the uniformly charged ring. This question is also very important. 2-3 बार बेटा आए हुए हैं, 2014, 15 I think and 13 में. So this question is also very important. ये भी बेटा आपके 3 या 5 marks में आते हैं, right? Then question number 4, derive an expression for torque on an electric dipole in a uniform electric field. This question is also very important. Okay, in 2000 I think 17 में question आया हुआ है बेटा. Okay. ओके 17 में भी आया हुआ और एक और साल आया हुआ है. So you have to derive the expression for torque when it is when dipole is placed in a uniform electric field. This question is also very important. Then next question number 5, define electric field lines. Draw pattern of electric field lines for various charges and charge distribution. This question is also very important for different distribution of charges, how electric fields are drawn. You have to draw electric field lines. Then question number 6, define electric flux. Write its SI unit, whether it is a scalar or vector quantity. All these things you have to study. Okay. Then last question number 7, and it is the most important question. One question, 5 marks comes in the exam from this topic, Gauss theorem, right? In 2016, 2017, then 2018. In all these years, this question comes. Okay, 2018, 5 marks, right? So 3 or 5 marks questions comes from this topic, application of Gauss theorem, state Gauss theorem, and how it is used to find electric field due to infinitely long straight uniform charged wire of linear charge density lambda. And second, uniformly charged infinite plane sheet. Plane sheet is also very important, right? Very important. कुछ भी पढ़ो नहीं पढ़ो बेटा, लेकिन ये तो पढ़ना ही है. Gauss theorem, right? And electric field on the axis of uniformly charged ring and electric dipole axial and equatorial position. बहुत important है questions. इनसे questions आने ही है board exams में. So I'm going to discuss how you write the solution of these questions in the board exams, right? किस तरीके से आप लिखोगे तो आपको नंबर मिलेंगे. So I am going to solve all these questions one by one. Let us start with question number 1. What is question number 1? State Coulomb's law and express it in vector form, right? Then what is Coulomb's law? How you write in vector form? So before starting this question, you must know about charge. What is charge? Actually, charge is an intrinsic property of any matter, right? It is an intrinsic property which gives rise to electric force between various objects. Suppose there is a charge body. If any charge or neutral body comes near this charge body, another charge body, suppose Q2 charge, and this is charge Q1. If any neutral or charge body comes near this charge body, what happens? This experiences some force due to this charge body. So charge is an intrinsic property of matter which gives rise to electric force between various objects, right? And also charge is a scalar quantity, right? And its SI unit is Coulomb. So you must know about charge. Now starting with this, what is Coulomb's law? How you write Coulomb's law? Suppose there are two charge bodies, Q1 and Q2. These two are point charges. The size of these charges are very small, or it is placed very far from us, so that it looks like point charges. Now if the distance between these two charges, suppose, is R, right? So this charge again exerts some force on this charge body, and this Q2 charge again exerts some force on this charge Q1, right? And what is the value of that force which this charge exerts on this one and this charge exerts force on this one? So according to Coulomb's law, it states that force of attraction or repulsion depending upon the sign of the charge. Charges are of two types, positive and negative. Like charge always repel and unlike charge always attract. So there is a force of attraction or repulsion between these 2 point charges, and it is directly proportional to product of the charges and inversely proportional to square of distance between them. It means the force of attraction or repulsion between these two charges is directly proportional to product of charges Q1 into Q2 and inversely proportional to square of distance. It means R square. You remove this proportionality, you get F equal to K Q1 Q2 by R square, right? This is scalar form of Coulomb's law, where K is a constant called electrostatic force constant and its value depends on nature of medium. Its value is given by K equal to 1 by 4 pi epsilon naught. Epsilon naught is permittivity of free space. And in free space its value is 8.85 into 10 to the power minus 12. Okay, and in 1 marks question generally comes what is the unit for this epsilon naught. Okay, so when you put this in place of K here 1 by 4 pi epsilon naught, then epsilon naught becomes what? Q1 Q2 by R square F, right? Q1 Q2 means Coulomb square by F into R square means Newton meter square. So unit for this epsilon naught, it means permittivity of free space is 8.85 into 10 to the power minus 12 Coulomb square per Newton meter square. You must remember this one, right? And for free space, when you put these values in this K equal to 1 by 4 pi epsilon naught, you get the value of K for free space is 9 into 10 to the power 9. And what is the unit for this one? K. Here, Newton meter square per Coulomb square, right? So, this is the unit for K. Its value is this one. So, according to Coulomb's law, force F equal to K Q1 Q2 by R square. Now, what is the direction of this force? This force always acts along the line joining these two charges, either in this direction, this one, or in this direction, only along the line joining the two charges, right? So, in this way, you write Coulomb's law. You have to remember this one. It is proportional to product of charges, inversely proportional to square of distance between them. Now, in exams, it comes as write Coulomb's law in vector form. So, vector form means what is the direction for this force? Force is a vector quantity. So, you must write Coulomb's law in vector form. Vector form, right? Suppose this is charge Q1, this one is charge Q2. This charge Q1 exerts force on this charge Q2. Okay, and these two charges are positive charges. So this Q1 charge exerts force on Q2 and repel each other. Both have same sign. So direction of force is along this one. This is F21. F21 means force on second charge. Due to which charge? First charge. First charge exerts force on second charge. So second charge experiences some force, that is F21. F21 means force experienced by charge Q2 due to charge Q1. And direction of force is this one, right? F21. And you know distance between these two is R. So in vector form you can write magnitude of R12 or R21. Both are same. Either you measure direction distance from this 1 to 2, R12, or from 2 to 1, same. So R equal to magnitude of R12 equal to R21, right? Now you have to write this, you have to written F21 equal to K Q1 Q2 by R square. Okay, but you have to write in vector form, you must show some direction also. This is the unit vector and this F21 is force on 2 due to 1. So 1 से लेके 2 तक unit vector is R12 from 1 to 2. In some books it is written R12 in place of R12, R2 minus R1, final minus initial, right? Okay. So this R12 is a unit vector from 1 to 2 and it's your direction of F21. Right? So simply write Coulomb's law, F equal to K Q1 Q2 by R square, and force on 2 due to 1 from 1 to 2. Direction is from charge 1 to charge 2. And you know unit vector, you can write unit vector by magnitude, right? R12 by magnitude of R12. Similarly, this Q1 charge also experiences some force due to this Q2 charge, right ना? Q2 के कारण भी Q1 पे force लगेगा and force इस direction में लगेगा F12. F1 is force on this Q1 charge 1 due to second charge F12 and this force from 2 to 1. So you write unit vector R21. Okay. So from here it's clear that this R12 is from this direction, 1 say 2, and R2 is in this direction. So both are in opposite direction, right? Unit vector is also in opposite direction. So this force F21 must be equal opposite to F12. It means it is in accordance with third law of motion also. In this way you write Coulomb's law and in vector form. Okay. Now come to second question. Electric field due to electric dipole at an axial position. Okay. Before starting this question, you must know about electric dipole. What is electric dipole? What is its value? Then you find electric field, right? Electric dipole. Actually, it is a system of two equal and opposite charges. Suppose there is a minus q charge and there is plus q charge, right? And separated by some distance. Suppose I am taking twice because mid of when you half this distance, it becomes a no fraction value. So for simplification, I am always taking distance between these two charges, twice of A or twice of D, anything you can take. So a system of two equal and opposite charges separated by some distance forms electric dipole. Okay, एक equal positive charge and negative charge दोनों की value same है and separated by distance, तो ये क्या बनाता है? Electric dipole, right? And its value is given by dipole moment. It is represented by small p, right? This dipole moment is given by q into 2a, distance between the two charges. And this direction of dipole moment is always from negative charge to positive charge. Direction is always from negative to positive, right? So this is the expression for dipole moment, P equal to Q into 2A. ये आपको याद रखना है क्योंकि ये अभी हम यूज करेंगे. Electric field, you know, the region around the charge in which any other charge comes experiences some force, right? And you have to find electric field intensity along axial position of this dipole. And then second part, equatorial position. So what is axial position and what is equatorial position? Axial position are actually points lying on the axis of the dipole. Suppose this is the dipole, minus q plus q. So axis is this one, right now? So at any point you have to find electric field along the axis. And what is equatorial? It is perpendicular bisector of this dipole. This is dipole plus q minus q, and perpendicular bisector is this one. So these are this point, this point, this point are all are equatorial position, right? You have to find electric field at these two positions. So first I am going to derive electric field intensity at an axial position, right? So first you draw this diagram. There is a dipole minus q plus q charge separated by a distance 2a, and the direction of this dipole movement is from negative charge to positive charge. This one is dipole movement, right? Okay. Now you have to find electric field at an axial position. Axial position is line joining the two charges. So line joining two charges, this one. At this point P, you have to find electric field intensity. You know electric field, the region around any charged body is what? In which any other body comes, it experiences some force. That region is called electric field. So there are two charges here, minus q and plus q charge. Due to this plus q charge, also there is electric field around this. And due to this minus q charge, also there is electric field around this region. So what is the net charge at point P? So you have to calculate electric field due to this positive charge also, due to this negative charge also, and then you have to calculate net electric field. Okay. For this, suppose this P is at a distance of r from the center of the dipole. This one is center of dipole, right? From here to this point P, suppose distance is r. Now you know what is the expression for electric field, force point charge due to charge q, k q by r square. R is the distance between the charge and the point at which electric field is to be determined. So here I have to calculate the electric field at point P due to this plus q charge also and minus q charge also. So what is the distance of this plus q charge to this point P? From the midpoint of the dipole, distance is r, and this total length of dipole is 2a. So this one becomes how much? This one becomes a, right? Total is r and this one is a. So from this plus q charge, distance becomes r minus a, right now, to the point P. Again, due to this negative minus q charge, what is distance of this minus q charge to point P? From the center to point P, distance is r, and from this to this, distance is what? A. So total distance becomes r plus a from minus q charge. Now if you know the distance and charge, you can easily find electric field. So electric field due to this plus q charge means this one, distance is r minus a. So kq by r minus a whole square. And the distance, direction of this electric field is away from this positive charge. Direction of field is always away from the positive charge and towards the negative charge. You must remember this one also, okay? So due to this plus q charge, direction of electric field is away from that charge. It means this direction, right? Now due to minus q charge, distance is r plus a. So kq by r plus a square. And due to negative charge, direction of field is towards that charge. So direction of electric field due to minus q is towards left. Now you know, smaller the distance, greater the field. So which distance smaller, r minus a or r plus a? Yes, r minus a is smaller. So electric field intensity due to plus q charge is greater than due to minus q charge. So E plus Q is greater than electric field due to minus Q. Now you have to calculate net electric field. This E plus Q minus electric field due to minus Q charge. You put these two values, right? KQ, this plus Q charge, KQ by R minus A square minus due to minus Q charge, KQ by R plus A square. You take the LCM of this one, R minus A square, R plus A square. Then here you take KQ common. Here in the denominator R minus A square. So here in the numerator R plus A square minus here R minus A square. Then you open this one using the formula A plus B whole square. Then these terms cut, R square minus R square, A square minus A square. Only 2RA, 2RA, it means 4RA is left. And you know what is dipole moment in terms of P? Dipole moment is product of charge into separation between the two charges. It means Q into 2A. And direction is from negative to positive charge. So here 2A. So only 2R is left here. Right now, if you take 2A separate from this side, 2A and into Q, 2A into Q is P, so 2R is left here, twice K, R is left here, and you write Q into 2A is P. So 2KPR by R minus A square whole square. This is the expression for electric field intensity, and its direction, net electric field, is in which direction? Electric field due to positive charge is greater than due to negative charge. So resultant is also is in this plus Q charge in this direction. So net electric field is also in this direction. And this is the direction of what? Electric dipole moment, right now. So electric field due to an axial position is in the direction of dipole moment. You can write this one. If R is very greater than A, if the size of the dipole is very small in compared to distance at which electric field is determined, in that case you neglect this A square, then it only becomes R square whole square, right? One R is cancelled here, you get 2 Kp by Rq. This is the expression for electric field intensity, twice Kp by Rq. So you must remember this one, it's very important. It must come in the exams, right? Now, how this electric field varies with R? Inversely proportional to R na? So, electric field and R, 1 marks question also come, draw the graph between E and R. So, you draw like this one. Electric field decreases as distance increases, right? And in that vector form, you can write electric field, direction of electric field is the direction in which dipole moment is there. So, you write it vector form also. In this way, this question you have to solve, electric field due to electric dipole. Now come to electric field at an equatorial point of a dipole. You have to calculate electric field due to at an equatorial position, right? Equatorial position means perpendicular bisector of this dipole. Suppose this is a dipole minus q plus q separated by a distance 2a, and this is perpendicular bisector of this dipole, right? Okay. You take this distance centered to this point P is R, and this one becomes how much? A. Bisector na? Adha adha hai beta, this side be A or this side be A. So this distance becomes minus q2 plus q, because I want distance from the two charges. I have to calculate electric field at this point P, total electric field due to this dipole na. So due to minus q charge, distance is under root r square plus a square, and due to this plus q charge, distance is r square plus a square by Pythagoras theorem. This r is a, so total is under root r square plus a square. This is x, right? Now electric field due to this plus q charge, direction of field is away from the charge, so direction is this one. This is electric field due to plus q charge, and this one is minus q charge, so direction of electric field is towards the negative charge. So this is direction of electric field due to minus q charge, right? Now electric field due to plus q charge is given by kq by x square. X is what? Under root r square plus a square. A है ना, इसका whole square. It is away from plus q charge. Due to minus q charge, kq by distance is again, distance is same. Here also under root r square plus a square. Here also r square plus a square. So here electric field is again this one. Direction is towards negative charge. But these two are not in the same direction, not exactly opposite direction. There is some angle between these two electric fields. So how you calculate the electric field? You have to resolve this electric field into its two components. One is along, one is perpendicular. Suppose this angle is theta, right? So this angle is also theta. Yes, na? And this angle is also theta. This electric field E due to plus q charge has two components. One is EP sin theta and another one is E cos theta. Then due to minus q charge also, one is E sin theta, another one is E cos theta. From here it's clear that E sin component theta is equal and opposite, right? Electric field is same. Let's see again, once again. Electric field here is also E, value is the same, and this one is also E. But these two are equal and opposite, so sign components cancel each other. Only this E cos theta in the same direction. So net electric field becomes twice E cos theta. Now what is the value for this cos theta in this figure? Let us see. Cos theta is what? Here is the triangle, suppose this is triangle, this one is theta. Cos theta is base by hypotenuse. It means A by x, right now? A by x. And x is what? Under root r square plus a square. So net electric field is twice. E is what? Twice. E is kq by this one r square plus a square under root whole square. So this under root becomes, okay, whole square means this under root and this whole square, it only becomes r square plus a square into cos theta. Cos theta is a by under root r square plus a square. When you solve this one, here power is 1, here in this power is 1 by 2. So 1 plus 1 by 2 is 3 by 2. So in this way twice kqa by r square plus a square 3 by 2. What is this twice qa? This is dipole moment P. So you can write twice qa, in place of this one you write P. So kp by r square plus a square 3 by 2. Here again direction of electric field is in this direction. Net electric field is in this direction now. It means from plus q to plus q, minus q, and dipole moment is from minus q to plus q. So direction of electric field is opposite to the direction of dipole moment here, right now. Direction of electric field is opposite to direction of dipole moment, right? Again, if distance r is greater than a, then you neglect this a square So only r square 3 by 2, 2 cancel, r cube is left, kp by r cube. And in vector form you can write minus kp by r cube. This minus sign shows direction of electric field is opposite to the direction of dipole moment. Here it's clear that the electric field along equatorial position is kp by r cube and along axial position is twice kp by r cube. So what is the relation between these two electric field? E axial is twice of E equatorial. Right. In this way you write this question. Okay. So two questions I have completed. One is Coulomb's law, another one is electric field due to electric dipole along axial and equatorial position. Now come to question number 3, electric field on the axis of charged ring. Okay. Here this is a uniform ring where charge is distributed uniformly, right? So we know that due to a charge, what is the value of electric field? But here there is not one charge. There are large number of charges uniformly distributed over this ring. So, and you have to calculate, this is the center of the ring. And along the center of the ring, there is an axis, right? This is the axis of the ring, at which here, at this point P, you have to calculate electric field. Now here total electric field is due to all the charges present on this ring, but there are large number of charges. So how you calculate electric field, how you apply Coulomb's law, that is valid only for point charge. So just you take one section of this ring where charge element is small dq, right? Small amount of charge. Suppose radius of this ring is A and the distance from the center to the point at which electric field is determined is suppose x. Now you have to calculate electric field at point P due to this small charge element dq. So you join the line from this charge to this point P and let us take that distance is r, and r becomes what? Radius is A and this one is x. So this is under root a square plus x square. So distance from the charge to the point where electric field is determined is r. Now due to this point charge, this is a positive point charge, so electric field at point P is away from that charge and along the line joining that charge. So this is the direction for electric field due to this charge dq. Sorry, you write here dE. Okay, by mistake it is written dE. Now again suppose this is the theta between this x and r. So this x is this axis and this r is this one. So if this one is theta, then this angle is also theta, vertically opposite angle. Now this is the direction for small electric field due to small charge dq. So this can be resolved into two components. One is along this one, and d cos theta, and this one is d sin theta, right? Again you take another charge element opposite to this one, right? Diametrically opposite charge element you take. Suppose first charge element you have taken this one, so you take this charge which is present diametrically opposited. This charge element also, there is an electric field at this point and this is in this direction d, right? If this one is theta, then this angle is also theta. So this has two components, this becomes d cos theta and this one is d sin theta. Electric field is same at these 2 points d, d, because distance is same. This one is also r, this one is also r. Charge is same, so electric field is same, but direction is opposite. So net electric field at this point P is this sine component cancel out each other, both are in opposite direction. Only cos component can be added. So total electric field is only due to this cos component, not due to sine component. Again you take this point and again diametrically opposite end this point. Both has electric field at this point equal electric field, but only it contributes cos component, not sin component. So you can say that at every charge element only cos component is present, sin component cancel out each other. So total electric field is just integration of that cos component d cos theta. Right now component, because sin component cancel out each other, only cos component is left. So component of d is what? K dq by r square, and only cos component is present. Now you have to find d cos theta all over the ring. So you just integrate over the ring de cos theta to get total electric field, right? This E net equal to this one, K dq by r square cos theta. Here for each charge element, distance r is same, radius is same, and from the set to the point at which electric field is determined, that is also same. It means theta is also same. So you take all these outside, K cos theta r square, only left is integration of dq. Integration of dq means a small dq all over the ring. So total charge over the ring, suppose capital Q is here. So dq total charge becomes capital Q. So your answers becomes, and this cos theta is what from that figure? From this figure, cos theta is this x by r. Right now, base by hypotenuse. So cos theta is x by r. Photo is not so clear. So here E net is K by r square. In place of cos theta, you write x by r and dq charge Q. So in this way, K Q x by r Q. And r is what? Under root x square plus a square. So final equations becomes E net equal to, it's not so clear, K Q x by x square plus a square 3 by 2, right? This is the final expression for electric field due to this uniform charged ring, right? E net is this one. Now there are different cases. What is the field at the center of the ring? Center of the ring, distance x is 0. So you put x equal to 0. Then this equation becomes what? This x is also 0. So net electric field is 0, right? Now for x greater than a, when x is very larger than a, it means x square is greater than a square. A square can be neglected. If you neglect this a square, then what is left? X square 3 by 2 is left. Okay, x square 3 by 2, this 2 to 2 cancel, x cube is left, k q x by x cube, 1x is cancel each other. Then final answer becomes k q by x square, right? So net electric field when x is very greater than a becomes k q by x square. It means it behaves like a point charge. Due to point charge, what is the net electric field? K q by r square. Here at a distance x, k q by x square. So this is case 2. Again, when r tends to infinity, again net electric field is 0. In this way, we solve this question, electric field due on the axis of the charge ring. So we have completed 3 questions: Coulomb's law, electric dipole, axial equatorial position, then electric field on the axis of charged ring. Now come to next question number 4, related to torque. You have to derive an expression for torque when dipole is placed in a uniform electric field. So what happens when you place one dipole? This is dipole minus q plus q charge, and you place this dipole in this uniform electric field. When all the lines are equidistant from each other, a straight line, this shows uniform electric field. At every point, electric field is constant. And in this electric field, you placed one dipole in this way, right? This side minus q and this side plus q. Okay. So, and separation between these two charges is twice t, right? So this one is minus q plus q separated by a distance 2d. Now the dipole moment direction is from which to which? Negative to positive direction. So dipole moment is in this direction. Now you place this dipole in this electric field. What happens? At the two ends, due to this electric field, right? Here minus q charge, here plus q charge, separated by distance 2d. Electric field direction is this one, right? This is the direction for electric field. Okay, and due to this electric field, this charge experiences some force. And what is force due to electric field? F equal to E into Q, right? So plus Q charge experiences force in this direction and minus Q charge experiences force in this direction, right? So these two forces are equal and opposite. They are cancel each other, but they are not at the same point. One is acting on this side, the other is acting at this point. So both forces acts at different points. So net force is 0, but it forms couple and it exerts torque on the dipole due to this electric field and the force experienced by this dipole. So it produces rotational motion. One force is in this direction, other force is in this direction, and it produces rotational motion in the dipole. It means it exerts some torque when dipole is placed in electric field. What is the value of that torque? Force is in linear motion and torque produces rotational motion. Torque is force into perpendicular distance between the two charges. These two are charges and perpendicular distance between the two charges is this one. Suppose this one is positive charge, this here is negative charge. So this is the perpendicular distance between the two charges. And what is its value? This dipole length is 2a, right? And it makes angle theta with the field direction. This is angle theta. This is direction of field, right? Here also theta is there. So the value of this perpendicular distance is, this is 2a3. So this perpendicular by hypotenuse is sine theta. So this becomes 2a sine theta, right now? Right? This perpendicular distance is 2a sine theta. So what is torque? Torque is force into perpendicular distance. Force is what? Q into E. And perpendicular distance means this AC. This is 2a sine theta. QE into 2a sine theta. This Q into 2a becomes dipole moment P. So this becomes P sine theta, right? And in vector form, you can write torque is a vector quantity. This P cross E is P sine theta. And what does it mean? What is the direction of this torque? P cross E. It means the dipole try to orient from P in the direction of E. So this is, here is negative charge, right? Here is positive charge. So this is the direction of dipole moment right now, and this one is direction of electric field, and this dipole try to orient P cross E means from P to E, and P to E perpendicular to P to E is this one. This is direction of torque. So when any dipole is placed in a uniform electric field, then that electric field, what? It exerts some torque on the dipole, and this torque tends to rotate the dipole in the direction of field. Torque tries to orient this dipole in the direction of this field. Okay, the main aim, when you put a dipole in a uniform electric field, that dipole experiences torque, and that torque try to orient the dipole in the direction of what? In the direction of field from P to E. So this is the formula for torque, P sine theta or P cross E. And here also different cases are there. Maximum torque is when theta is 90 degree. It means field is in this direction and dipole is placed 90 degree to this field. Minus PQ is here. plus Q is here, right? And this is direction of electric field. Then in this case, maximum torque experienced by the dipole. It try to orient themselves in the direction of field 90 degree, right? Minimum torque when theta is 0 degree or 100 degree. In both the cases, 0 degree means dipole is also in this direction, dipole moment, and E is in also this direction, right? It means this side is minus Q charge, this side is plus Q. Direction is minus 2 plus. So direction of P and E are same. In this case also torque is minimum rotational motion, because they are already in the direction of electric field. So where it goes, and if E is in this direction and P is opposite to this one, it means minus Q is this side, plus Q this side. So dipole moment direction is from P to Q. Dipole moment is in this direction and electric field is in this direction. Here 180 degree angle, again sine 180 is 0, so minimum torque. But again there are two conditions. It generally comes in 1 or 2 marks questions: stable equilibrium and unstable equilibrium. When you say that the body is in a stable equilibrium, when body slightly moves and come down to its original position. If the angle between P and E is 0, so if slightly push the body, it try to orient in the direction of field. In this case, minimum torque is there when theta is 0 and it is stable equilibrium. Body come to its original position. But when theta is 180 degree, then in that case what happens? Body does not return to its own position. Body is in this direction, field is in this direction. So when it is placed in this field, it try to orient in the direction of field, and once it comes in the direction of field, it does not return back to its own position opposite to this one. So it means it is unstable equilibrium. So these questions also comes in 3 or 5 marks. Torque experienced by the dipole when it is placed in a uniform electric field, and also conditions for stable and unstable equilibrium. So in this way, we have completed 4 questions, and then come to next question number 5, electric field lines and their properties. Question number 5. Electric field lines are pictorial representation of electric field. Actually, suppose there is a charge plus Q, and if you due to this charge there is electric field around this charge, but what is the direction of electric field, what is the magnitude of electric field, we don't know. So this electric field lines is just pictorial representation of that electric field. Suppose you put a test charge at this point. In whatever direction this test charge is moving, that is the direction of electric field. So the path followed by this test charge is nothing but electric field lines. And due to this positive charge, you find that the charge moves in this direction like this way. This is the direction of electric field lines due to this positive charge, right? So you can define electric field lines in this way. These are imaginary lines, smooth continuous curves, and it represents the presence of electric field in a region. Whatever the direction in which this test charge is moving, that gives direction of electric field at that point, right? So these are just imaginary concepts, not real concepts. What are different properties of these electric field lines? These field lines begins at positive charge and ends at negative charge. It always starts from the positive charge and ends at, suppose here is a negative charge, ends at negative charge. It means it originate from the positive charge, always away from the positive charge, and always towards the negative charge, right? These lines are continuous but do not form closed loops. Suppose this is a positive charge and this one is negative charge. Field lines is always from positive to negative, right? This is direction of field lines. This is direction of field lines, positive to negative, but it do not form closed loop. This field lines is from this positive charge to this negative charge. This one is for this positive charge to this negative. It do not form closed loops, right? You must remember this one. The relative closeness of the field lines gives magnitude of electric field. Suppose this is plus Q charge and there are number of field lines, right? These are electric field lines due to this positive charge. Greater the closeness of this field lines, it represents greater magnitude of the electric field. As the field lines moves away from each other, they move far apart from each other. It means at this place there is a weak field, and at this place they are nearer to each other. It means there is a strong field near the charge. So the relative closeness of the field lines gives magnitude of electric field at that point. Also, the tangent at any point on the field lines gives direction of electric field. If you want to find a direction at any point, you just draw one tangent at that point. The tangent, suppose this is a path followed by the test charge. So the tangent drawn at this point gives direction of electric field, right? These are different properties. One important property is that the two field lines never intersect each other. This question also comes in 1 marks. Why two field lines never intersect each other? Suppose this is plus Q charge and this one is minus Q charge, and field lines is away from the positive charge and towards the negative charge. But these two field lines never intersect each other. If these two field lines, suppose this one is going like this one, other is coming like this one. If these two field lines intersect each other, then at the point of intersection, two tangents are drawn. It means two direction of electric field at the same point, which is not possible. So if two lines intersect, then there will be two directions of electric field at the point of intersection. That's why the two field lines never intersect each other. The field lines are always perpendicular to the surface of conductor. It is always perpendicular to the surface of conductor. Suppose this is a conductor, then field lines is always perpendicular to this surface of conductor. It is at 90 degree, right? Now again one important question comes. Draw electric field lines for different charge system, for positive charge, negative charge. So I told you already that due to positive charge the field lines moves away from the positive charge. Closer these field lines, stronger is the magnetic field. Far apart these field lines, weaker is the magnetic field. Same for negative charge also, but direction is towards the negative charge. These are direction of field lines. For pair of unlike charges, suppose one is positive, one is negative. So field lines is like this one, from positive to negative. For a pair of two like charges, the field lines are like this one. Due to this positive charge, the field lines moves in this way, and due to this positive, field lines moves in this way. Because these two field lines never intersect, these two are repel each other and moves in this direction. So due to these two positive charges, field lines are like this one. It don't goes like this one. Okay, because these field lines are repelled by the field lines produced by this positive charge, and two field lines never intersect each other. So due to two like charges, field lines are going like this one. Is it clear? So this question is also very important. In this way, we have completed 5 questions. Now come to next question. Define electric flux and its SI unit. What is electric flux? Okay. Electric flux. Electric flux is number of field lines passing perpendicular to the plane surface. Suppose I am taking this 2D figure, right? This is length and this one is suppose breadth of rectangle or anything. Okay, this is 2-dimensional figure. So what is the area of this one? Area is length into breadth. This is area. Here there is one another important term, that is area vector. The area vector is always normal to this area, right? Suppose this is a plane, this is area of this shape, rectangle, right? Area vector is normal either outward or inward. So in case of 2 dimension, area vector is whether it enters or it comes out of the surface. We are taking both, inward and outward, both in case of 2 dimension. But in case of 3 dimension, suppose this is a cube, right? Cube, this is a closed surface. 3 dimension, 2 dimension is open surface, 3 dimension is closed surface. In this case, again we take only outward normal, not area vector which is entering to the surface, those which are leaving to the surface, normal to the surface. So in 3 dimension we take only outward normal. Like up now, suppose some lines are passing through this plane. So how many number of lines passing through this plane? This is nothing but electric flux. Electric flux is number of field lines passing perpendicular to the plane. This is plane, and perpendicular to it, this is either inward or outward. Perpendicular to this one, right now. Suppose this is a plane and perpendicular to this plane is this one, right? So how many number of lines passing through this plane or perpendicular to this plane, or you can say in the direction of area vector, because area vector is always normal to the area. So if lines are passing along the area vector direction or perpendicular to the line, this plane, it means maximum lines passes. If you rotate the plane, then number of lines passing through that plane decreases. It means how many number of lines passing through a particular plane depends upon area vector, right? Also on angle, and also the direction of electric field, in which direction electric field is there. Or in all these factors, this number of lines depends. It means number of lines means electric flux. So electric flux is product of area and component of electric field normal to the area vector. E cos theta ds, it means E dot ds. Just revise this one. This flux is represented by phi and it is equal to E dot ds. It means E ds cos theta. When angle between this ds is area vector and this one is electric field, both are in the same direction, maximum flux. But if these are normal to each other, in that case minimum flux is there. And this area vector is always normal to the area. This electric flux is a scalar quantity. Its SI unit is Newton meter square per coulomb, right? And flux for closed surface, we always write phi equal to, this is a symbol for closed surface, right? Suppose this is a closed surface. At this place E dot ds, at this place E dot ds, at this place E dot ds. Total flux through this closed surface is given by phi total is E dot ds integration of this closed surface. This is for closed surface. We always write flux equal to phi equal to E dot ds, right? This question is also important. It may generally comes in 1 or 2 marks, right? After this electric flux, one very important question, that is Gauss theorem. Here I am written, flux is maximum when electric field is normal to the area. Electric field is normal to the area means electric field is along the area vector, because area and area vector are perpendicular to each other. So if electric field and area vector are in the same direction, then that case maximum flux is there. Okay. Next, Gauss theorem. What is this Gauss theorem? Actually, Coulomb's law is also used to determine electric field, but in case of complicated circuit, we can't determine the electric field using Coulomb's law. For that one, for complicated circuit, if we want to calculate the electric field, we use this Gauss theorem and calculation becomes very simple. What is this Gauss theorem? It states that the total flux over a closed surface is 1 by epsilon naught times the net charge enclosed by the surface. Suppose this is a closed surface, any closed surface. So total flux, how much total flux is there in this closed surface? It is total flux is always equal to total charge enclosed by the surface divided by epsilon naught. Q is the total charge enclosed inside this surface, right? and this phi is equal to, for closed surface, E dot ds. It means phi equal to E dot ds surface integral close equal to q by epsilon naught. This is Gauss theorem, and using this theorem we can easily calculate electric field. But this theorem is only applicable if the surface is closed, right? This total flux does not depend upon the shape and size of the surface. Just surface is closed, either a small closed surface or big closed surface. If total charge is q, it means total flux is q by epsilon naught. So it depends upon that the surface is closed and how much charge is enclosed by that surface, right? Wait. Okay, suppose there is a closed surface and inside that closed surface dipole is placed. So what is the flux now due to this dipole enclosed inside the closed surface? Net charge is how much? Q inside is plus Q minus Q, 0. So net flux is also 0. Right now, suppose there is a cube. This is a cube. So what is the net flux enclosed by this cube? Whatever is the shape and size of the surface, if charge is q, okay, so net flux is q by epsilon naught. If I ask what is the flux through this one surface, so how many surfaces in the cube? 6 surfaces. So flux through one surface is what? 1 by 6 q by epsilon naught, right? Total flux is q by epsilon, but through one surface it's only 1 by 6 times q by epsilon. And this Gauss theorem is used to determine electric field for complicated circuits, where we can't simply, using Coulomb's law, we can't find the electric field. This question is very, very, very important. 5 marks questions comes from this one. There are 2 applications for Gauss law. One is related for this year, removed from their syllabus, that is for spherical shell, only electric field due to infinitely long straight charged wire, infinite plane sheets. 2 applications are there and both are important. So let us discuss one by one. First one is to calculate electric field due to an infinitely long straight charged wire. Okay. Let us consider a long infinite charged wire. Here this is an infinite long charged wire. Charge is distributed uniformly over this wire. Now you have to calculate electric field due to this charged wire. So for this you have to apply Gauss theorem, because Coulomb's law is used only for point charges. Here there is not only one charge, there are number of charges. So we have to apply Gauss theorem. And there are some conditions for applying Gauss theorem so that it becomes easy to calculate electric field. First is charge must be enclosed within a surface, and that surface is called Gaussian surface, so that you can apply Gauss theorem. Also, the electric field at the point where you have to calculate must be symmetric at all points of Gaussian surface. The surface which you are imagining, that is Gaussian surface, electric field at every point on that Gaussian surface should be symmetric, equal or constant, or you can say electric field is same, right? Gaussian surface does not pass through the charge. Charge must be enclosed within that Gaussian surface. So how you draw Gaussian surface in case of long infinite wire? Suppose this is a wire and you know that at equal distance due to this charge there is a field at this point, r distance, due to this charge there is a field at this point. So all equal distance, r distance, the field is same at all these points. Again, due to this positive charge, field is at this point, equal distance r, field is at this point, at all these points field is same, symmetric. So if we have to draw Gaussian surface like this one, cylindrical surface. This cylindrical surface is Gaussian surface in case of this one. Why we draw this cylindrical surface? Because only on this curved surface equal distance from this wire, so charge is constant on this surface, so that we can easily apply Gauss theorem. Now consider this point, okay, this point. Now at this point area vector is normal to this surface, yani ki dA is this one, area vector is this one, and also electric field due to this charge is also along this direction, same. It means area vector and electric field is along the same direction. So easily we can apply Gauss theorem, and you have to find electric field at this point due to this whole charged wire. Okay, so suppose this is one surface, right? This one is curved surface is another, and this base is another surface. There are three surfaces, top, bottom, and this curved surface, right? Now we have to calculate flux through all these three surfaces. Total flux through this surface is the flux passing through each surface, top surface, bottom surface, and this curved surface, right? So electric flux, total electric flux of this Gaussian surface is phi1 plus phi2 plus phi3. Phi1 is electric flux through this surface, and here you find that electric field is in this direction, and area vector is always normal to the area. So electric area vector is in this direction, and here angle between electric field and area vector is 90 degree for this first surface. The second surface, electric field and area vector are in same direction, so 0 degree angle. And in third surface also, electric field is in this direction and area vector is in this direction. It means at this surface also 90 degree. Now we have to find total flux first. So flux through first surface is E dot ds, and E dot ds is what? E ds cos 90 degree, and cos 90 is 0. So this term is 0 through first surface. Third surface also 90 degree angle. This term is also 0. Only this term is left. E ds cos 0. Cos 0 is what? 1. So only total flux through the second surface is left. E ds cos 0 is 1. E is constant. E is same everywhere on the Gaussian surface. You take E outside, and this ds is surface area of this lateral surface, curved surface. And suppose length of this cylinder is L, and at a distance R, radius of this is R, base of the cylinder is. So at a distance R, you have to calculate electric field. So area of this cylinder is curved surface area is 2 pi RL. So total flux is phi equal to E dot 2 pi RL, equation number 1. Now you have to apply Gauss law. Total flux through this enclosed surface is always Q by epsilon naught, right? One more thing, in case of linear charge distribution, we always take linear charge density. Total charge is Q, but what is the charge per unit length? For that one, I have taken this linear charge density. This is charge per unit length. So total charge of this wire Q is how much? Lambda into L. So you put in place of Q, lambda into L, flux becomes lambda L by epsilon naught. Equation number 3. You must remember this linear charge density in case of uniformly charged wire. In case of plane sheet, that is 2 dimension, we have to take surface charge density. Here 1 dimension, linear charged wire, so linear charge density. From this 1 and 2, both have flux E dot 2 pi RL equal to lambda L by epsilon naught. Okay. So this LL cancel. E equal to lambda by 2 pi epsilon naught R. This is the electric field due to an infinitely long charged wire. Lambda by 2 pi epsilon naught R. And also in 1 marks question, this comes generally as draw electric field with distance R. So here E is inversely proportional to R. So draw electric field like this one. E decreases with increase in distance R, right? In this way. So this first application, electric field due to infinitely long straight charge wire. This is very, very important. You must remember that in case of this straight charge wire, you always draw cylinder, right? Which is Gaussian surface. Then you have to take three surface, top, bottom and this lateral surface. Then you have to find the flux through all these three surfaces. Then apply Gauss theorem, because Gauss theorem is only apply if the surface is closed, enclosing that charge, right? And also Gaussian surfaces like that one, so that electric field remains constant on the Gaussian surface. In this way you solve that question. Second and last important application of Gauss theorem is electric field due to an infinite plane sheet of charge. This is one plane sheet of charge. Again, we have to calculate electric field due to this plane sheet of charge. So, suppose there is a plane sheet, it is in two dimension. For this case also, electric field at equal distance at this point is same everywhere. Electric field at this point is same everywhere. So, you draw a Gaussian surface flat cylinder, right? Here, due to this positive charge, electric field is in this direction. Due to this positive charge, electric field is in this direction, right? And area vector is always normal to this surface, this direction. Here also in this direction. And area vector of this lateral surface is this perpendicular to this surface. And electric field is this direction. So in this case also there are three surfaces. One, this one is 2, and this one is third surface. Now we have to calculate total flux first through all these three surfaces, phi 1 plus phi 2 plus phi 3. In first surface, electric field and area vector are in same direction, angle is 0. Here electric field area vector makes 90 degree angle, and in this third surface also 0 degree, right now. So if angle is 90 degree, it means cos 90 is 0. So there is no contribution of flux or passing through this surface. Second surface flux is 0. Only first surface and third surface plus flux is passing through these two surfaces. So total flux becomes twice, this term becomes 0, twice E ds, cos 0 is 1. E is constant everywhere on that surface, so twice you take outside, surface integral of this ds. ds is the total surface area of that surface, right? These two, first and this third surface. So here I have taken area, total surface area is A. So you write total flux becomes 2EA is total area of the plate. Now apply Gauss theorem. You can easily apply because charge is enclosed within that cylinder and E is symmetric everywhere on that surface. So we apply Gauss law, phi equal to Q by epsilon naught. Q is net charge enclosed by the Gaussian surface. Here plate, so surface charge density is used. Surface charge density, charge per unit area. I have forgotten to write here. Charge per unit area. So this charge becomes sigma into A. You put this charge here in place of Q, sigma A. Phi becomes sigma A by epsilon naught. This is equation number 3, and equation 1 is phi equal to 2EA. So 2EA equal to sigma A by epsilon naught. From here you calculate E equal to sigma by 2 epsilon naught. So here you can easily find that E is not dependent on R. In the first application, uniformly long charged wire, E is inversely proportional to R square. R. Here E is independent on R. It means electric field remains same on near points of thin sheet. If sheet is positively charged, the field is directed away from it right now. Here this plate is positively charged. So field is away from this plate. If this plate has negatively charged, charge density is negative, the field is towards this plate, right? Okay. In this way, we solve this one. Okay. And I think it's clear to you. All these are very, very important from the examination point of view. Just remember one thing, in case of thin plane sheet, you have to draw flat cylinder. In that one, a straight cylinder. Just these two things keep in mind and calculate easily electric field due to these two things. Okay, so theory part is over. I will try to make another video for numerical part also. So with this, if you want these type of videos for other chapters also, please write in the comment box and share to your friends also. Okay students, so these are all about 7 most important questions of chapter 1. Please keep revising and stay tuned with this channel. Thank you.